Okay, I think we're live. Let's see. Are we? Yep, we're live. It's showing up on YouTube. Let me just check. Yep. Okay. So this is gonna be a shorter stream. I was at work earlier, and I was able to finish the problem set. So the whole DFS algorithm, I was able to finish it at work. I'm just gonna show the code right now. Let's see, Safari. Yep, and then there we go. Okay, so there we go. This is get best path. So I had to make best distance non-local, and then I referenced it inside my DFS, right? So this basically references this one, and then the main problem with our code before was the whole pop thing. So I was popping inside this, and then this only popped whenever I found like a new path. However, I wanted to pop regardless, right? And then in here, I don't want to change total back to zero, right? I want to subtract it from the, so if it's ABC, right? And then we pop C out. So I want to subtract the value of C from total and the value of the outdoors from the respective value of C, right? So that's what we did. And then, yeah, then I converted it into tuple because that's what they wanted for the problem set. And then directed DFS is pretty easy. It's just basically calling this function with its given parameters, right? So we did that. This works. We passed all the test cases. So guess we're chilling. This problem set was heavy. I was expecting me to take around like 4 hours. I think it took me double that, or almost double that. So around 8 hours, I would say somewhere in 6 to 7 hours. So clearly it took more time than I thought, but whatever. So I'm gonna watch lecture 6, which is Monte Carlo simulation.
The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources.
Also, if I end up getting it, if I get like a high-paying job, I'm donating hella money to MIT OCW. They're so goated.
For free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Welcome to Lecture 6. As usual, I want to start by posting some relevant reading. For those of you who don't know, this lovely picture is of the casino at Monte Carlo. And shortly you'll see why we're talking about casinos and gambling today. Not because I want to encourage you to gamble your life savings away. A little history about Monte Carlo simulation, which is the topic of today's lecture. The concept was invented by the Polish-American mathematician Stanislaw Ulam, probably more well known for his work on thermonuclear weapons than on mathematics, but he did do a lot of very important mathematics earlier in his life. The story here starts that he was ill, recovering from some serious illness, and was home and was bored and was playing a lot of games of solitaire, a game I suspect you've all played. Being a mathematician, he naturally wondered, what's the probability of my winning this stupid game which I keep losing? And so he actually spent quite a lot of time trying to work out the combinatorics so that he could actually compute the probability. And despite being a really amazing mathematician, he failed. The combinatorics were just too complicated. So he thought, well, suppose I just play lots of hands, count the number I win, divide by the number of hands I played. And then he thought about it and said, well, I've already played a lot of hands and I haven't won yet. So it probably will take me years to play enough hands to actually get a good estimate, and I don't want to do that. So he said, well, suppose instead of playing the game, I just simulate the game on a computer. He had no idea how to use a computer, but he had friends in high places, and actually talked to John von Neumann, who is often viewed as the inventor of the stored program computer, and said, John, could you do this on your fancy new ENIAC machine? And on the lower right here, you'll see a picture of the ENIAC. It was a very large machine. It filled a room. And von Neumann said, sure, we could probably do it in only a few hours of computation. Today, we would think of a few microseconds. But those machines were slow. Hence was born Monte Carlo simulation. And then they actually used it in the design of the hydrogen bomb. So it turned out to be not just useful for cards. So what is Monte Carlo simulation?
That's interesting.
It's a method of estimating the values of an unknown quantity using what is called inferential statistics. And we've been using inferential statistics for the last several lectures. The key concepts, and I want to be careful about these because we'll be coming back to them, are the population. So think of the population as the universe of possible examples. So in the case of solitaire, it's a universe of all possible games of solitaire that you could possibly play. I have no idea how big that is, but it's really big. Then we take that universe, that population, and we sample it by drawing a proper subset. Proper means not the whole thing. Usually more than one sample to be useful, certainly more than zero. And then we make an inference about the population based upon some set of statistics we do on the sample. So the population is typically a very large set of examples, and the sample is a smaller set of examples. And the key fact that makes them work is that if we choose the sample at random, the sample will tend to exhibit the same properties as the population from which it is drawn. And that's exactly what we did with the random walk, right? There were...
So I'm guessing you need to do that like a large number of times for it to be accurate to the mathematical representation.
A very large number of different random walks you could take of, say, 10,000 steps. We didn't look at all possible random walks of 10,000 steps. We drew a small sample of, say, 100 such walks, computed the mean of those 100, and said, we think that's probably a good expectation of what the mean would be of all the possible walks of 10,000 steps. All right, so we were depending upon this principle. And of course, the key fact here is that the sample has to be random. If you start drawing the sample and it's not random, then there's no reason to expect it to have the same properties as that of the population. And we'll go on throughout the term and talk about the various ways you can get fooled and think you have a random sample when exactly you don't. All right, let's look at a very simple example. People like to use flipping coins because coins are easy. So let's assume we have some coin. All right, so I brought two coins, slightly larger than the usual coin. And I can flip it once, and let's consider one flip, and let's assume it came out heads. I have to say, the coin I flipped is not actually a $20 gold piece, just in case any of you were thinking of stealing it. All right, so we've got one flip. And it came up heads, and now I can ask you the question, if I were to flip the same coin an infinite number of times, how confident would you be about answering that all infinite flips would be heads? Or even if I were to flip it once more, how confident would you be that the next flip would be heads? And the answer is not very. Well, suppose I flipped the coin twice, and both times it came up heads. And now I asked you the same question. Do you think that the next flip is likely to be heads? Well, maybe you would be more inclined to say yes than having only seen one flip, but you wouldn't really jump to say sure. On the other hand, if I flipped it 100 times, and all 100 flips came up heads, well, you might be suspicious that my coin only has a head on both sides, for example, or is weighted in some funny way that it mostly comes up heads. And so a lot of people, maybe even me, if you said I flipped it 100 times and it came up heads, what do you think the next one will be? My best guess would be probably heads. How about this one? So here I've simulated 100 flips, and we have 50 heads here, 2 heads here, and 48 tails. And now if I said, do you think that the probability of the next flip coming up heads is at 52 out of 100? Well, if you had to guess, that should be the guess you make. Based upon the available evidence, that's the best guess you should probably make. Because you have no reason to believe it's a fair coin. Could well be weighted. You know, we don't see it with coins, but we see weighted dice all the time. Or we shouldn't, but they exist. You can buy them on the internet. So typically, our best guess is what we've seen. But we really shouldn't have very much confidence in that guess. Because, well, could have just been an accident. Highly unlikely, even if the coin is fair, that you'd get 50-50, right? So why, when we see 100 samples and they all come up heads, do we feel better about guessing heads for the 101st than we did when we saw 2 samples? And why don't we feel so good about guessing 52 out of 100 when we've seen 100 flips that came out 52 and 48? And the answer is something called variance. When I had all heads, there was no variability in my answer. I got the same answer all the time. And so there was no variability, and that intuitively and, in fact, mathematically should make us feel confident that, okay, maybe that's really the way the world is. On the other hand, when almost half are heads and almost half are tails, there's a lot of variance. Right? It's hard to predict what the next one will be. And so we should have very little confidence that it isn't an accident that it happened to be 52-48 in one direction. So as the variance grows, we need larger samples to have the same amount of confidence. All right, let's look at that with a detailed example. We'll look at roulette. In keeping with the theme of Monte Carlo simulation. This is a roulette wheel that could well be at Monte Carlo. There's no need to simulate roulette, by the way. It's a very simple game. But as we've seen with our earlier examples, it's nice when we're learning about simulations to simulate things where we actually can know what the actual answer is so that we can then understand our simulation better. For those of you who don't know how roulette is played, is there anyone here who doesn't know how roulette is played? Good for you. You grew up virtuous. All right. So, well, all right. Maybe I won't go there. All right, so you have a wheel that can spins around, and in the middle are a bunch of pockets. Each pocket has a number and a color. You bet in advance on what number you think is going to come up or what color you think is going to come up. Then somebody drops a ball in that wheel, gives it a spin. And through centrifugal force, the ball stays on the outside for a while, but as the wheel slows down, it heads towards the middle. And eventually, it settles in one of those pockets, and you win or you lose. Now, you can bet on it. And so let's look at an example of that. So here's a roulette game. I've called it fair roulette because it's set up in such a way that, in principle, if you bet, your expected value should be 0. You'll win some, you'll lose some, but it's fair in the sense that it's not either a negative or a positive sum game. So, as always, we have an underbar in it. Typically, well, we're setting up the wheel with 36 pockets on it. So you can bet on the numbers 1 through 36. That's the way range works, you'll recall. Initially, we don't know where the ball is, so we'll say it's none. And here's the key thing is, if you make a bet, this tells you what your odds are. That if you bet on a pocket and you win, you get len of pockets minus 1. So this is why it's a fair game, right? You bet $1. If you win, you get $36, your dollar plus 35 back. If you lose, you lose. All right, self.spin will be random.choice among the pockets. And then there's simply bet, where you just can choose an amount to bet and the pocket you want to bet on. I've simplified it. I'm not allowing you to bet here on colors. All right, so then we can play it. So here's play roulette. I've made game the class a parameter because later we'll look at other kinds of roulette games. You tell it how many spins, what pocket you want to bet on. For simplicity, I'm going to bet on the same pocket all the time. Pick your favorite lucky number and how much you want to bet. And then we'll have a simulation just like the ones we've already looked at. So the number you get right starts at 0. For I in range number of spins, we'll do a spin. And then tote pocket plus equal game.bet pocket. It'll come back either 0 if you've lost or 35 if you've won. And then we'll just print the results. So we can do it. In fact, let's run it. So here it is. I guess I'm doing a million games here, so quite a few. Actually, I'm going to do 2. I'm going to look what happens when you spin it 100 times, what happens when you spin it 1,000,000 times. And we'll see what we get. So what we see here is that if we do 100 spins, the first time I did it, my expected return was minus 100%. I lost everything I bet. Not so unlikely, given that the odds are pretty long, that you do 100 times without winning. Next time I did 100, my return was a positive 44%, and then a positive 28%. So you can see for 100 spins, it's highly variable what the expected return is. That's one of the things that makes gambling attractive to people, right? That if you go to a casino, 100 spins would be a pretty long night at the table. And, maybe you'd won 44%. You'd feel pretty good about it. What about 1,000,000 spins? Well, people aren't interested in that, but the casino is, right? They don't really care what happens with 100 spins. They care what happens with 1,000,000 spins. What happens when everybody comes every night to play. And there what we see is, you'll notice, much less variance. Happens to be minus 0.04, plus 0.6, plus 0.79. So it's still not 0, but it's certainly, these are all closer to 0 than any of these are. We know it should be 0, but it doesn't happen to be in these examples. But not only are they closer to 0, they're closer together. There's much less variance in the results, right? So here I show you these three numbers and ask, what do you expect to happen? You have no clue, right? So I don't know. Maybe I'll win a lot. Maybe I'll lose everything. I show you these three numbers. You're going to look at it and say, well, you know, it's going to be somewhere between 0, around 0, and maybe 1%. But you're never going to guess it's going to be radically different from that. And if I were to change this number to be even higher, it would go even closer to 0. But we won't bother. OK, so these are the these are the numbers we just looked at, because I'd set the seed to be the same. So what's going on here is something called the law of large numbers, or sometimes Bernoulli's law. This is a picture of Bernoulli on this stamp. It's one of the two most important theorems in all of statistics, and we'll come to the second most important theorem in the next lecture. Here it says, in repeated independent tests with the same actual probability, the chance that the fraction of times the outcome differs from p converges to 0 as the number of trials goes to infinity. So this says if I were to spin this fair roulette wheel an infinite number of times, the return would be 0. The real true probability from the mathematics. Well, infinite is a lot, but 1,000,000 is getting closer to infinite. And what this says is the closer I get to infinite, the closer it will be to the true probability. So that's why we did better with 1,000,000 than with 100. And if I did 100 million, we'd do way better than I did with 1,000,000. I want to take a minute to talk about a way this law is often misunderstood. This is something called the gambler's fallacy. And all you have to do is say, let's go watch a sporting event, and you'll watch a batter strike out for the 6th consecutive time. The next time they come to the plate, the idiot announcer says, well, he struck out 6 times in a row. He's due for a hit this time, because he's usually a pretty good hitter. Well, that's nonsense. It says people somehow believe that if deviations from expected occur, they'll be evened out in the future. And we'll see something similar to this that is true, but this is not true. And there's a great story about it. This is told in a book by Huff and Geis. And this truly happened in Monte Carlo with roulette. And you could either bet on black or red. Black came up 26 times in a row. Highly unlikely, right? 2 to the 26 is a giant number. And what happened is word got out on the casino floor that black had kept coming up way too often. And people more or less panicked to rush to the table to bet on red, saying, well, it can't keep coming up black. Surely the next one will be red. And as it happened, when the casino totaled up its winnings, it was a record night for the casino. It just, millions of francs got bet because people were sure it would have to even out. Well, if we think about it, probability of 26 consecutive reds is that. A pretty small number. But The probability of 26 consecutive reds when the previous 25 rolls were red is what? No, that. No. If you'd had 25 reds and then you spun the wheel once more, the probability of it having 26 reds is now 0.5, because these are independent events, unless, of course, the wheel is rigged, and we're assuming it's not. People have a hard time accepting this, and I know it seems funny, but I guarantee there will be some point in the next month or so when you will find yourself thinking this way, that something has to even out. I did so badly in the midterm, I will have to do better on the final. That was mean. I'm sorry. All right. Speaking of means, ooh. See, Professor Grimm's not the only one who can make bad jokes. There is something, it's not the gambler's fallacy, that's often confused with it, and that's called regression to the mean. This term was coined in 1885 by Francis Galton in a paper of which I've shown you a page from it here. And the basic conclusion here was what this table says is if somebody's parents are both taller than average, it's likely that the child will be smaller than the parents. Conversely, if the parents are shorter than average, it's likely that the child will be taller than average. Now, you can think about this in terms of genetics and stuff. That's not what he did. He just looked at a bunch of data. And the data actually supported this. And this led him to this notion of regression to the mean. And here's what it is, and here's the way in which it is subtly different from the gambler's fallacy. What he said here is following an extreme event, parents being unusually tall, the next random event is likely to be less extreme. He didn't know much about genetics, and he kind of assumed the height of people were random. But we'll ignore that. Okay, but the idea is here that it will be less extreme. So let's look at it in roulette. If I spin a fair roulette wheel 10 times and get 10 reds, that's an extreme event, right? There's a probability of basically 1 over 1024. Now, the gambler's fallacy says if I were to spin it another 10 times, it would need to even out, as in I should get more blacks than you would usually get to make up for these excess reds. What regression to the mean says is different. It says it's likely that in the next 10 spins, you will get fewer than 10 reds. You will get a less extreme event. Now, it doesn't have to be 10. If I'd gotten 7 reds instead of 5, you consider that an extreme, and you would bet that the next 10 would have fewer than 7. But you wouldn't bet that it would have fewer than 5. All right? Because of this, if you now look at the average of the 20 spins, it will be closer to the mean of 50% reds than you got from the extreme first spins. So that's why it's called regression to the mean. The more samples you take, the more likely you'll get to the mean. Yes?
So roulette wheel spins are supposed to be independent. So
Yes.
It seems like the second 10 should.
Pardon?
It seems like the second 10 times that you spin it,
Yeah.
like that shouldn't have anything to do with that.
Has nothing to do with the first one.
Like you said, it's likely that you'll get like fewer than 10 reds.
Right, because you have an extreme event, which was unlikely. And now if you have another event, it's likely to be closer to the average than the extreme was to the average. Right? And it's precisely because it is independent. Does that make sense to everybody? Yeah.
Isn't that the same as the gambler's fallacy then? By saying that, like, because this was super unlikely, the next one should return to normal?
No, the gambler's fallacy here, and it's a good question, and indeed people often do get these things confused. The gambler's fallacy would say that the second 10 spins we would expect to have fewer than 5 reds because you're trying to even out the unusual number of reds in the first spin, right? Whereas here we're not saying we would have fewer than 5, we're saying we'd probably have fewer than 10, that it'll be closer to the mean, not that it would be below the mean. Whereas the gambler's fallacy would say it should be below the mean to, quote, even out the first 10. Does that make sense? Okay, great questions. Thank you. All right, now, you may not know this, but casinos are not in the business of being fair. And the way they don't do that is in Europe, they're not all red and black. They sneak in one green. And so now if you bet red, well, sometimes it isn't always red or black. And furthermore, there's this 0. They index from 0 rather than from 1. And so you don't get a full payoff. In American roulette, they managed to sneak in 2 greens. They have a 0 and a double 0. Tilting the odds even more in favor of the casino. So we can do that in our simulation. We'll look at European roulette as a subclass of fair roulette. I've just added this extra pocket 0. And note
Be back.
I have not changed the odds. So what you get if you get your number is no higher, but you're a little bit less likely to get it because we snuck in that 0. Then American roulette's a subclass of European roulette in which I add yet another pocket. All right, we can simulate those. Again, nice thing about simulations, we can play these games. So I've simulated 20 trials of 1,000 spins, 10,000 spins, 100,000, and 1,000,000. And what do we see as we look at this? Well, right away we can see that fair roulette is usually a much better bet than either of the other two. That even with only 1,000 spins, the return is negative. And as we get more and more, as I got to 1,000,000, it starts to look much more like closer to 0. And these, we have reason to believe at least, are much closer to your true expectation, saying that while you break even in fair roulette, you'll lose 2.7% in Europe and over 5% in Las Vegas or soon in Massachusetts. All right. We're sampling, right? That's why the results will change, and if I ran a different simulation with a different seed, I'd get different numbers. Whenever you're sampling, you can't be guaranteed to get perfect accuracy. It's always possible you get a weird sample. That's not to say that you won't get exactly the right answer. I might have spun the wheel twice and happen to get the exact right answer of the return. Actually, not twice, because the math doesn't work out, but 35 times and gotten exactly the right answer. But that's not the point. We need to be able to differentiate between what happens to be true and what we actually know in a rigorous sense is true, or have maybe don't know it, but have real good reason to believe it's true, right? So it's not just a question of faith. And that gets us to what's in some sense the fundamental question of all computational statistics, is how many samples do we need to look at before we can have real justifiable confidence in our answer? As we've just seen, not just a few minutes ago with the coins, our intuition tells us that it depends upon the variability in the underlying possibilities. So let's look at that more carefully. We have to look at the variation in the data. So let's look at first something called variance. So this is variance of x. Think of x as just a list of data examples, data items. And the variance is we first compute the average of value. That's mu. So mu is for the mean. For each little x and big X, we compare the difference of that and the mean. How far is it from the mean? And square the difference, and then we just sum them. So this takes how far is everything from the mean? We just add them all up. And then we end up dividing by the size of the set, the number of examples. Why do we have to do this division? Well, because we don't want to say something has high variance just because it has many members, right? So this sort of normalizes by the number of members, and this just sums how different the members are from the mean. So if everything is the same value, what's the variance going to be? If I have a set of 1,000 sixes, what's the variance? Yes? Zero.
And just, you think this is going to be hard, but I came prepared.
I was hoping this would happen. Look out. I don't know where this is going to go. All right. Maybe it isn't the best technology.
I'll go home and practice.
All right, so, and then the thing you're more familiar with is the standard deviation. And if you look what the standard deviation is, it's simply the square root of the variance. Now, let's understand this a little bit and first ask, why am I squaring this here? Especially because later on I'm just going to take the square root anyway. Well, squaring it has one virtue, which is that it means I don't care whether the difference is positive or negative, right? And I shouldn't, right? The variance, I don't care which side of the mean it's on. I just care it's not near the mean. But if that's all I wanted to do, I could take the absolute value. The other thing we see with squaring is it gives the outliers extra emphasis, because I'm squaring that distance. Now, you can think that's good or bad, but it's worth knowing it's a fact. The more important thing to think about is standard deviation all by itself is a meaningless number. You always have to think about it in the context of the mean. If I tell you the standard deviation is 100, you then say, well, and I ask you whether it's big or small, you have no idea. If the mean is 100 and the standard deviation is 100, it's pretty big. If the mean is 1 billion and the standard deviation is 100, it's pretty small. So should never want to look at just the standard deviation. All right, here's just some code to compute those, easy enough. Why am I doing this? Because we're sort of now getting to the punchline. We often try and estimate values just by giving the mean. So we might report on an exam that the mean grade was 80. It's better, instead of trying to describe an unknown value by an unknown parameter by a single value, say the expected return on betting a roulette wheel, to provide a confidence interval. So what a confidence interval is a range that's likely to contain the unknown value and a confidence that the unknown value is within that range. So I might say on a fair roulette wheel, I expect that your return will be between -1% and +1%. And I expect that to be true 95% of the time you play the game, if you play 100 rolls, spins. If you take 100 spins of the roulette wheel, I expect that 95% of the time your return will be between this and that. So here we're saying the return on betting a pocket 10,000 times in European roulette is -3.3%. I think that was the number we just saw. And now I'm going to add to that this margin of error, which is plus or minus 3.5% with a 95% level of confidence. What does this mean? If I were to conduct an infinite number of trials of 10,000 bets each, my expected average return would indeed be minus 3.3%, and it would be between these values 95% of the time. Right? I've just subtracted and added this 3.5. Saying nothing about what would happen in the other 5% of the time. How far away I might be from this. This is totally silence on that subject. Yes?
I think you want 0.2, not 9.2.
Oh. Let's see. Yep, I do. Thank you. We'll fix it on the spot. This is why you have to come to lecture rather than just reading the slides, because I make mistakes. Thank you, Eric. All right, so it's telling me that, and that's all it means. And it's amazing how often people don't quite know what this means. For example, when they look at a political poll and they see how many votes somebody is expected to get, and they see this confidence interval and you say, what does that really mean? Most people don't know. But it does have a very precise meaning, and this is it. How do we compute confidence intervals? Most of the time, we compute them using something called the empirical rule. Under some assumptions, which I'll get to a little bit later, the empirical rule says that if I take the data, find the mean, compute the standard deviation as we've just seen, 68% of the data will be within one standard deviation in front of or behind the mean. Within one standard deviation of the mean. 95% will be within 1.96 standard deviations. And that's what people usually use. Usually when people talk about confidence intervals, they're talking about the 95% confidence interval, and they use this 1.6 number. And 99.7% of the data will be within 3 standard deviations. So you can see if you're outside the 3rd standard deviation, you are a pretty rare bird, for better or worse, depending upon which side. All right, So let's apply the empirical rule to our roulette game. So I've got my 3 roulette games as before. I'm going to run a simple simulation. And the key thing to notice is really this print statement here. All right, that I'll print the mean, which I'm rounding. And then I'm going to give the confidence intervals, plus or minus, and I'll just take.
Someone's calling me, just 1 second. Okay, my roommate was calling me, but yeah, let's continue.
Standard deviation times 1.6 times 100. Why times 100? Because I'm showing you percentages. All right? So again, very straightforward code. Just simulation, just like the ones we've been looking at. And, well, I don't think I'll bother running it for you in the interest of time. You can run it yourself. But here's what I got when I ran it. So when I simulated betting a pocket for 20 trials, we see that of 1,000 spins each, for 1,000 spins, the expected return for fair roulette happened to be 3.68%, a bit high. But you'll notice the confidence interval, plus or minus 27, includes the actual answer, which is 0. And we have very large confidence intervals for the other 2 games. If we go way down to the bottom, where I've spun the wheel many more times, what we'll see is that my expected return for fair roulette is much closer to 0 than it was here. But more importantly, my confidence interval is much smaller, 0.8. So now I really have constrained it pretty well. Similarly, for the other 2 games, you will see maybe it's more accurate, maybe it's less accurate, but importantly, the confidence interval is smaller. So I have good reason to believe that the mean I'm computing is close to the true mean, because my confidence interval has shrunk. So that's the really important concept here, is that we don't just compute the value in the simulation. We use, in this case, the empirical rule to tell us how much faith we should have in that value. All right. The empirical rule doesn't always work. There are a couple of assumptions. One is that the mean estimation error is 0. What is that saying? That I'm just as likely to guess high as guess low. In most experiments of this sort, most simulations, that's a very fair assumption, right? There's no reason to guess I'd be systematically off in one direction or another. It's different when you use this in a laboratory experiment, where in fact, depending upon your laboratory technique, there may be a bias in your results in one direction. So we have to assume that there's no bias in our errors. And we have to assume that the distribution of errors is normal. And we'll come back to this in just a second, but this is a normal distribution called the Gaussian. Okay. Under those two assumptions, the empirical rule will always hold. All right, let's talk about distributions, since I just introduced one. We've been using a probability distribution. And this captures the notion of the relative frequency with which some random variable takes on different values. There are two kinds, discrete, and these when the values are drawn from a finite set of values. So when I flip these coins, there are only two possible values, head or tails. And so if we look at the distribution of heads and tails, it's pretty simple. We just list the probability of heads. We list the probability of tails. We know that those two probabilities must add up to 1. And that fully describes our distribution. Continuous random variables are a bit trickier. They're drawn from a set of reals between two numbers. For the sake of argument, let's say those two numbers are 0 and 1. Well, we can't just enumerate the probability for each number. How many real numbers are there between 0 and 1? An infinite number, right? And so I can't say for each of these infinite numbers what's the probability of it occurring. Actually, the probability is close to 0 for each of them. Is 0 if they're truly infinite. So I need to do something else. And what I do that is what's called the probability density function. This is a different kind of PDF than the one Adobe sells. So there, we don't give the probability of the random variable taking on a specific value. We give the probability of it lying somewhere between two values. And then we define a curve which shows how it works. So let's look at an example. So we'll go back to normal distributions. This is, for the continuous normal distribution, it's described by this function. And for those of you who don't know about the magic number e, this is one of many ways to define it. But I really don't care whether you remember this. I don't care whether you know what E is. I don't care if you know what this is. What we really want to say is it looks like this. In this case, the mean is 0. It doesn't have to be 0. I've shown as a mean of 0 and a standard deviation of 1. This is called the so-called standard normal distribution. But it's symmetric around the mean. And that gets back to it's equally likely that our errors are in either direction, right? So it's peaks at the mean. The peak is always at the mean. That's the most probable value. And it's symmetric about the mean. So if we look at it, for example, and I say, what's the probability of the number being between 0 and 1? I can look at it here and say, all right, let's draw a line here and a line here. And then I can integrate the curve under here. And that tells me the probability of this random variable being between 0 and 1. If I want to know it between -1 and 1, I just do this, and then I integrate over that area. All right, so the area under the curve, in this case, defines the likelihood. Now I have to divide and normalize to actually get the answer between 0 and 1. So the question is, what fraction of the area under the curve is between -1 and 1? And that will tell me the probability. So what does the empirical rule tell us? What fraction is between -1 and 1, roughly? Yeah, 68%, right? So that tells me 68% of the area under this curve is between -1 and 1, because my standard deviation is 1, roughly 68%. And maybe your eyes will convince you that's a reasonable guess. Okay, we'll come back and look at this in a bit more detail on Monday of next week, and also look at the question of why does this work in so many cases where we don't actually have a normal distribution to start with.
Okay, so that was pretty complicated, I would say. It was really probability and math heavy, but it was interesting, right? The whole gambler's theorem, whatever, and then how the probability are like independent, right? So even if we get like 10 red, the next one is just half, right? If there's two variables. And then the counter theorem, right, where we're less likely to get 10 red for the next 10, but we will be closer to the mean, right, which is going to be 5. So yeah, and the whole standard deviation, and then the normal distribution, where you can basically find the area under the curve for continuous probability, and for discrete probabilities it's just 0.5, and 0.5 will add to 1, right? So we just want the whole area under the curve is just basically just gonna get added to 1. Okay, so with that being said, we're gonna do the third problem set right now. Or we're gonna attempt to do it. I'm gonna spend around 2 hours ish trying to solve it, and hopefully I can solve it in that time. I don't expect to solve it in 2 hours, but I'm gonna attempt it for 2 hours and then maybe watch another lecture video. But before that, I gotta do a quick errand, so I'll be back. Okay, so we are back for like 10 minutes. I'm gonna have to leave for 10 minutes. But let's start on problem set 3. I had to run like a huge errand for my roommate. But let's look at it. Okay, let's see at first the PDF, right? Okay, so PDF. There we go. Okay, full screen. Holy. Okay. In this problem set, you'll design a simulation and implement a program that uses class to simulate robot movement. We recommend testing your code incrementally to see if your code is not working as expected. Test your code, run PST underscore test underscore f16.py. As always, please do not change any given function signatures. Okay. Make sure you consult the style guide, as we will be taking point deductions for violations, example non-descriptive variable names and uncommented code. Bro, if I was like an actual student at MIT, this would cook me, but nonetheless. You'll be using Python's random module, so check out its documentation. Sure. Make sure you import random at the top of your file. Some useful functions called include random.randint. So for integer inputs a and b returns a random integer n, such as so any random integer inclusive of a and b and anything in between. Random.random returns a float n such that it's between 0 and 1. Random.seed0 starts a pseudo random number generator Python uses at the same spot, so that the sequence of random numbers it produces from different runs of your code will be the same. You may find using this is useful while debugging. Fair enough. So the same spot, so that the sequence of random number produces from different runs of your code will be the same. Okay, I get that. Okay, now let's see the simulation itself. iRobot is a company started by MIT alumni and faculty that sells the Roomba vacuuming robot. Watch on the product videos to see this robot in action. Okay, we'll do that later. Roomba robots move around the floor, cleaning the area they pass over. Okay. Your code will simulate. You will code a simulation to compare how much time a group of Roomba-like robots will take to clean the floor of a room using two different strategies. The following simplified model of a single robot moving in a square 5x5 room should give you some intuition about the system we are simulating. A description and sample illustrations are below. Okay. The robot starts out at some random position in the room. Okay. Its direction is specified by the angle of motion measured in degrees clockwise from north. So, okay, so like this. Its position is specified from the lower left corner of the room, which is considered to be the origin 0, 0. So this is 0, 0. The illustrations below show the proposed position indicated by a black dot, as well as its direction indicated by the direction of the red arrowhead. Okay. The robot starts at position 2.1, 2.2. Okay, so 1, 2. So 2 here. I'm guessing this is X, this is Y. So, and then as we go up, with an angle of 205 degrees measured clockwise from the north. Okay. That's 205. This is clockwise, right? Yep. The robot has moved 1 unit in the direction it was facing. Oh, I see. So this is the angle part, right? So it's doing this. Okay. The robot has moved 1 unit in the position it was facing to the position 1.7, 1.3, cleaning another tile. Okay. The robot has moved 1 unit in the same direction 205 degrees from the north to the position 1.2, 0.4, cleaning another tile. The robot could not have moved another unit in the same direction without hitting the wall, so it instead it turns to face in a new random direction 287 degrees. So this way. Now the robot moves along its new direction to the position 0.3, 0.7, cleaning another tile. Simulation components. Here are the components of the simulation model. Rooms. Rooms are rectangles divided into square tiles. At the start of the simulation, each tile is covered in some amount of dirt, which is the same across tiles. You'll first implement the abstract class rectangular room in problem 1, and then you will implement the subclass empty room and furnished room in problem 2. Okay. Robots. Multiple robots can exist in the room. iRobot has invested in technology that allows a robot to exist in the same position as another robot without causing a collision. You'll implement the abstract class robot in problem 1. You'll then implement subclass standard robot and faulty robot in problems 3 and 4. More details of the properties of these components will be described later in the problem set. Helper code. We have provided 2 additional files and verify movement. This Python file contains helper code for testing your code and for visualizing your robot simulation. Do not modify them. If one of these files throws an error, it is because of an error in your code implementation. To test your code, run. Okay. Okay, the first part. Read ps3.py carefully before starting so that you understand the provided code and its capabilities. Remember to carefully read the doc strings for each function to understand what it should do and what it needs to return. Okay. Let's do that. Let's go to spider. There we go. Okay. ps3.py. So we have import math, import random, the visualize library, and then pylab. Okay, so we can test robot movement. So this is position. It's an x coordinate, y coordinate. We can get x, we can get y, and we can get a new position. Computes and returns a new position after a single clock tick has passed, and with this object as the current position and with the specified angle and speed. Okay, does not test whether the return position fits inside the room. So I see. Cool. And this is the str method. Just 1 second. I have a career fair tomorrow. Interesting. Okay. I'll be back in 5 minutes. Okay, we are back. Let's see. Okay, so problem on rectangular room. Rectangular room represents a rectangular region containing clean or dirty tiles. A room has a width and a height and contains width and height tiles. Okay, each tile has some fixed amount of dirt. The tile is considered clean only when the amount of dirt in the tile is 0. Okay, so initially a rectangular room with a specified width, height, and dirt amount on each table, and these are some constraints that we're given. Clean tile at position marks the tile under the position as clean by capacity. Amount of dirt assumes the pause represents a valid position inside the room. So it's a position object and capacity. The amount of dirt to be cleaned in a single time step can be negative, which would mean adding dirt to the tile. Note the amount of dirt on each tile should be non-negative. Okay. If the capacity exceeds the amount of dirt on the tile, mark it as 0. Is tile cleaned? Okay, returns true if the tile has been cleaned. Assumes that N and M are valid tile inside. Okay. False, otherwise the tile is considered clean only when the amount of dirt on this tile is 0. Get number of clean tiles, the total number of. Okay. Is position in room? If position is inside a room, get dirt amount. Okay. Get number of tiles. I think I understand that. Is position valid? True if position is in the room. False. And in the case of furnished room. Okay. And then we have a robot class, empty room class, furnished room class, faulty robot class. Okay, so as a lot of classes, I think it's better if I start reading the problem sets and start tackling these like one at a time and stuff, reading the whole entire thing a go. So let's see, back to problem set. Okay. Why can't I see it? I can't see. There we go. Okay. The first task is to implement 2 abstract classes, rectangular room and robot. An abstract class will never be instantiated and is instead uses a template for other classes. Okay, that inherit from it. Abstract class define methods that are shared by their subclasses. These methods can be implemented in the abstract classes, but they can also be left unimplemented and instead implemented in their subclasses. Okay. In the skeleton code provided, the abstract class contains some methods which should only be implemented in the subclasses. If the comment for the method says do not change, please do not change it. You can test your code as you go along by running the provided test cases. Okay. In PS3.py, we've provided skeletons for these classes, which you will fill in for problem 1. We've also provided you for your complete implementation of the class position. Okay, class description. Rectangular represents the space to be cleaned and keeps track of the tiles that have been cleaned. Okay, robot stores the position, direction, and cleaning capacity of a robot. Position represents the location in x and y coordinates. X and y are floats, satisfying. Okay, so it won't be it will be less than the width and then less of the height, right? Representation. You will need to keep track of which parts of the floor have been cleaned by the robot. When a robot's location is anywhere inside a particular tile, we will consider the dirt on the entire tile to be reduced by some amount determined by the robot. We will consider the tile to be clean when the amount of dirt on the tile is 0. We'll refer to the tiles using ordered pair of integers, 0, 0, 0, 1, etc. Tiles can never have a negative amount of dirt. Starting condition. If the entire floor is uniformly dirty, each tile should start with an integer amount of dirt specified by dirt amount. And then this is the robot implementation details. There's a lot of hints. Okay, let's read through it. Representation. Each robot has a position inside the room. We'll represent the position using an instance of the position class. Remember, the position coordinates are floats. A robot has a direction of motion. We'll represent the direction using a float direction satisfying 0 to 360, which gives an angle in degrees from north. Robot has a cleaning capacity. Capacity which describes how much dirt is cleaned on each tile at each time. Starting condition. Each robot should start at a random position in the room. The robot's room attribute has a method you can use. Okay, that's a hint. A robot moves according to its movement strategy, which you'll implement in update position and then clean. Okay. Note that room tiles are represented using ordered pair of integers, but a robot's position is specified as floats. Be careful converting between the two. Okay. If you can find any place above where the specification of the simulation dynamics seems ambiguous, it is up to you to make reasonable decision about how your program slash model will behave and document the decision in your code. Complete the rectangular room and robot abstract classes by implementing their methods according to the specifications in PSET. Remember that these classes will never be instantiated. We will only instantiate their subclasses. Okay. Make sure to think carefully, and these are some hints about what kind of data type you want to store information about the floor text in the rectangular room class. A majority of the methods should only require only one line of code. Okay. The robot class and the rectangular room class are abstract classes, which means that we'll never make an instance of them. Instead, we'll instantiate classes that inherit from the abstract class. Okay. In the final implementation of these abstract classes, not all methods will be implemented. Not to worry, their subclasses will be implemented. Example, robot subclasses will implement the method update position and clean. Okay. Remember that tiles are represented using ordered pair of integers. Given a position specified as floats xy, how can you determine which tile the robot is cleaning? So if it's like 2.1 and 3.2, it's gonna clean tile 2 and 3. So we're gonna basically do a floor of that number, right? Not a floor division, but like a floor. So round down the numbers basically. So even if it's at a 2.9, it's still gonna clean coordinate 2. Remember to give the robot an initial random position and direction. The robot's position should be of the position class and should be a valid position in the room. Note that the abstract class rectangular room has a get random position method that may be useful for this. Okay. Consider using math.floorx from the math module instead of int-x to round round floats to whole numbers. So the numbers are always rounded down and points are ensured to be inside the room. Yeah, that's what I was saying. So you use floor, right? Seems simple enough. Why did I close the window? I shouldn't have closed the window because I might. It's a lot of description, but doesn't look that daunting. So I think we can code it up, right? So back to spider. Better, right? Okay. I think we are ready to code that up. So let's start with rectangle, the init. So our integer has to be greater than 0. Height has to be greater than 0, and dart amount has to be greater than equal to 0. So let's start with an if statement. Self.width, we assign it to width. Self.height, we assign it to height, and then dart amount, we assign it to dart amount. Else we're gonna raise value error, or is it better to raise individual value errors? So for width, I don't think it matters that much. Your inputs don't meet the constraints. This is gonna be dart amount. Yep, that's init done. I don't know if there's like a separate test case for init. Might as well run the test case. I mean, there might be, right? Interesting. Seems you're trying to import a module. So import imp. Apparently it doesn't imp. This doesn't have the imp package. Okay, so it's a old library, right? So I have to migrate the entire code base. That's why we use AI. I'm gonna copy it and ask AI to basically migrate the whole code base, and hopefully it works. So import lib is what we use. And I mean, I suppose I could do it by myself, but I'd have to go through the whole documentation of import lib, and that's like a lot of work. And I don't need to do that. Like, I can just focus on the meat of the problem set. I am running Claude in the background for this, the test cases at least. So it's a lot of lines of code. But I don't think so they test the init, because yeah, just first it's testing. Yeah, I don't think so they're really testing the init at all. It's testing. Yeah. Yeah, they're not testing init. So I think we can move to the next part of the code while AI is trying to solve whatever, right? Okay. So oh, it's actually done, by the way. So suppose I can copy it and I hope that it works. And if it doesn't, then I'll find some way to get around this. It can't be that hard. Let's see. Bad magic number in text. Let's see. Okay, so it doesn't work. We'll work our way around this. So I'm guessing it's reading, because there's a lot of .py code here, and it's reading those, but I guess those expect to use imp, right? Yeah, so I think the better thing that I can do is just run it with Python 2.7, right? Okay, so I can just do terminal and then let's see. Okay, so I'm gonna have to quit Spider for now, and then so okay. So I'm installing Python 2 right now for this code to work. Um, yeah, okay, as long as that's happening, we can keep coding on Spider, I suppose, because it's happening on the background inside the terminal. Okay. PS3.py. Okay. Clean tile position marks the tile under the position pause as clean by capacity amount of dirt. Assume that pause represents a valid position inside this room. Pause position capacity, the amount of dirt to be cleaned in a single time step. Can be negative, which would mean adding dirt to the tile. Okay. The amount of dirt on each tile should be non-negative. If the capacity exceeds the amount of dirt on the tile, mark it as 0. Okay. So yeah, so there is something called get dirt amount, and position we can get x and y. So x comma y equals pause dot get yeah, I don't know if this should be valid syntax, right? So we're calling two methods at once, right? Pause.get underscore x, pause.get underscore y, right? So we have our x comma y here, and then so dart equals self dot get underscore dart amount x comma y, right? And then we have the dart, right? So if capacity is greater than dart, return or mark it as 0, right? So we have to mark that specific position having that dart 0. So is there a method for that? Get dart amount is position valid, get random position is position valid, get non-titles, get dart amount, position room, get, okay, so there is style clean. Okay, so there, okay, so mark it as 0. So I guess self dot dart underscore amount equals 0, else, because we're gonna have to modify it. It asks us to mutate it, equals to whatever amount we had. I can just do dart minus capacity. Yeah, should work, right? Let's see where we're at. Okay, we're down. Python for there is downloaded. So now okay. Okay, is tile cleaned? Assumes that m and n are valid tile inside the room. M is an integer, n is an integer, returns true if the tile m n is cleaned. False otherwise. Tile is only when the amount of dirt. So I have a so for this, right, sure we have a dirt amount, but I feel like we need another data structure for our init. So what I'm saying is we need this dirt amount is basically, yeah, this is not initializing some rectangular room, right? I mean, sure, we have our width, height, and then dirt amount, but we want each tile to have that dirt amount. That's what I'm saying. So it's going to be a different data structure. So perhaps a dictionary with x comma y as the key. Right? And then that dirt amount for each x comma y. That way we can mod. So that this is wrong. So let's see. So we can do for I in range width, for j in range height, right? Actually, it's gonna be the other way around. Height is gonna be the first thing because it's the height, and then it's gonna be the width because the x values is gonna be the one that changes at first. So width, right? And then basically what we'll do is in here we can write self dot rect, right? And then self dot rect I comma j equals dirt underscore amount, and that is definitely the way we should initialize this, right? And then in here we get xy, and then get dirt amount is something that we're gonna do later, right? And then now we're gonna do self dot rec x comma y equals dirt minus self dot rec x comma y, or in this case this is gonna be, we are basically cleaning it out completely, so that way each specific coordinate has its own dirt amount, right? Let's see. Okay, also run doing the Python thing on the side, so installing the correct version of Python so that we know what to run. Second, let's see software, Python installation files. Okay, so let's keep doing this. So is tile clean? Returns true if the tile mn has been killed. Assumes that mn represents a valid tile inside the room. Okay, so if mn has been clean, so this is gonna be one line: self dot rec m comma n equals 0, right? Get number of clean tiles, returns an integer, the total number of clean tiles in the room. So we just loop over our rect, right? And then yeah, so num equals 0 for, I'm just gonna do key comma value. I know probably we don't need the key, but actually, since we don't need, for value in self dot rect dot values gives us the values, right? I think items is key comma value, right? If value equals 0, num plus equals 1, and return num. Okay, simple enough. Version. I'm still trying to get the test case working, basically. Okay, so brew install tcl-tk. Okay, so as we're doing that, we can keep doing the problems. Oh, it's pretty fast actually. By nv uninstall y, there we go. Reinstall with support. Enter support. Okay. Now we can do is position in room. Pause or returns true if position is in the room. False otherwise. Okay, so I'm guessing as long as can we have a negative index? No, so we our width and height is greater than 0, and the way I'm doing it is it's always going to be positive, right? So it starts off with 0 0, right? Yes, and then even in the position it says it has to be 0 till width. So if whatever our position returned, the x values and the y values for position, if it's less than the width and height, right, then we should be chilling. So we can let's just do this self dot width equals width so that we can reference it later, right? And self dot height equals height. Okay, and now wait, before that let me try to get the test cases running. Okay. best case is a ordeal, but I suppose we can do it. Okay, it's downloading again. But this time it's position in room. Okay, so where were we at? Okay, so pos dot let's just copy this line x comma y. Okay, so this line is fine. Now if we can return let's see. I'm not gonna do this in one line because it's gonna be if x greater than 0 and I'm sure there's like a better way to do this, but might as well not. And x less than width, right? If y greater than 0 and y less than height, return true, otherwise basically return false. Oh yeah, self dot width and then self dot height. There we go. Yeah, so this is probably like not the best way to do it. I'm pretty sure there's like a cleaner one line way to do this, but I'm sure this way is correct. And might as well do the correct thing. Okay, get dirt amount assumes that m and n are valid tile inside the room. Returns an integer. Yeah, this is easy. Return self dot rec m comma n. Yep, that's one line. Do not change. Implement it in subclass. Okay, so we're basically done with the rectangular room. Now we need to do the robot thing. That's it, right? Then we'll pretty much be done with problem 1. Okay, so robot initializes a robot with a given speed and given cleaning capacity in a specified room. The robot initializes a random direction and a random position in the room. uh, room, a rectangular room object. Okay, speed, capacity. Okay. So let's do this. Random equals self dot get underscore random, actually room dot get underscore random position. Let me go back to test case. Okay, so I guess I need a Windows laptop for the test cases to be working, but for now let's just keep coding and then we'll do the test cases later, right? Okay, and I'm pretty sure whatever we wrote it should pretty much be okay, and then if not then we can debug it later. I'll just use my Windows laptop. Okay, so we have random, and now let's see. Let me see if I can share both for this application capture preview. There we go. Nope. Yeah, I wanted to move this somewhere else. Yeah, I think that's better. I'm really bad at editing. Okay, I mean, it works, I guess. So this is a problem set definition. Maybe if I do this, Nope. Whatever. Okay, I can move it around, so perhaps this is better, maybe. I mean, I can still see it. Okay, so okay, yeah, this is definitely better. Okay, okay, so robot, that's what we're doing. With position coordinates of floats, a robot has a direction of motion. Yes. Over the cleaning capacity. Robot has a speed. So if speed greater than 0, self dot speed equals speed, else raise value error. Speed has to be greater than 0. Okay, so we have speed and then a positive integer if capacity greater than 0, self dot capacity greater than 0, else error capacity can't be negative or 0. Okay, now speed and okay. Initial is a random direction and a random position in the room. So we have the random position from random position. Now we just need the random direction, which is going to be a number from 0 to 360, right? So greater than equal to 0, less than 360. So we can use the random. And is this going to be an integer or is it going to be a float? Okay, so it's going to be a float. Okay. So yeah, as angle equals to 360 times random dot, do we have random imported? We do have random imported, so I'm gonna name this as R instead. Random dot random, right? And this should work. And now let's try to think about this. So there's gonna be a position. It's gonna be inside that room. Direction of motion, or what is the cleaning capacity? I think we're done with the robot class, right? So we need to be able to access these values. So each robot has a position inside the room, right? So get random position, it returns a position object. So we have the position object. So yeah, so self dot r, as long as we can access these, and then self dot angle. So this is one instance of a robot, right? Returns the robot position, giving the robot's position in the room. Okay, so return self dot r. Actually, let's just name it pause. Yeah, self dot pause. Better naming, right? So okay, so same, should be one liner. Turn self dot angle. And now Set robot position. So set the position of the rope. Okay. Set robot position. So self dot pause equals position, right? Set robot direction. Yeah. So self dot angle equals direction, and that should be the robot class done. And I feel like this is where I'm gonna stop for today. I wanted to do more, but I had to run an errand, and for that it took a long time. But this doesn't seem that hard, like this problem set so far. Definitely seems easier than the DFS thing that we tried. And I think tomorrow I'm gonna do this in like a Windows laptop with the Python 3.5, because the test cases uses Python 3.5, and for Mac I need to use the latest Python models. Apparently, that's what I did. That's what I was doing. I was researching on how to run the test cases. So yeah, that's about it.